So what's to do today is to continue on the chapter 1, and we explain the statement, which is called the Caldera embedding theorem. Which is asking that if you have a complex manifold, X, okay, and the question is when does it sit inside CPN, for some large n. It's a complex submanifold. So when you have a holomorphic map, so it's like an embedding problem. If you are in real manifold, you're asking where since the Rn, complex manifold, compact, let's say. Then you have no holomorphic function. And then all you have is a twisted holomorphic function. Okay. And one remark is that if this happens as a corollary, that will imply that, in fact, X is defined by polynomials. So this is a rather non-trivial statement because this is just holomorphic function. In general, you have lots of holomorphic functions, and maybe exponential function. But once you sit inside here, then it's defined by polynomial, meaning that X is equal to some P1 equal to P2, some finite number of polynomial, let's say some K equal to 0, and then all these Ki's are homogeneous polynomial. So these are called the child field. So things are algebraic. Okay? A priori, it's just a holomorphic function, but if you sit inside CPN, the only one has to be polynomial. Okay? And so such things are called projective variety, smooth projective variety. And the theorem is this is true if and only if the following thing happens. Okay. If and only if you have a holomorphic lie bundle, and first of all, holomorphic lie bundle is described by when you know some section is holomorphic. Just like a manifold is a complex manifold is when you know a function is holomorphic functions. So that is controlled by having an operator called a d bar, okay, on the lie bundle whose square is 0. Okay. So that can control the complex holomorphic structure. And you have lots of holomorphic bundle, but then you need one with the following property that this one, you choose a metric so a bundle, it just means a family of complex vector space of one-dimensional. The family is a holomorphic family, but now each vector space has a Hermitian inner product. That's the statement. Okay. Then you can have such that its curvature is positive. Okay, so that is the conditions. Okay, and what's the curvature? The statement is once you choose these two statements. So let me say a word about here. Maybe I'll continue here. So it's a remark here. Okay. In general, not necessarily lie bundle, if you have a vector bundle, just any Hermitian vector bundle, not even complex manifold. This is it, not necessarily complex at the moment. Okay. And if you have a connections, okay. So last time I explained that what is a connection. A connection is a way that if you have any 2 points, if you choose a path from one point to another point, that gives you a identification. Okay? So it's a trivialization along any path. Okay? In a compatible way. That means you trivialize on the first half, the second half is the same as you trivialize. It's equivalent to the same as the trivialization along the whole composition. Okay? So that is a so-called parallel transport. And that if you say infinitesimally, it just move a little bit, infinitesimally. So that statement is what we usually call connections. Infinitesimally, meaning that if you choose a direction, just at a point, you choose a direction that tells us how to have a path a little bit. So you need to be able to identify the space a little bit. So once you pick this one, then you should get the identifications of the vector space. So that is the same as you choose a sections. So fix a V, fix a vector field V. Okay. Then you map this one to that one. You have to identify the section at this point to a nearby one. Okay. But this one has to have a property that the compositions, you can just compose the identifications. So that property is the same as this looks like a derivative. So this has to satisfy. If you have a section, and then if you have a functions, then this is the same as the vector field act on the function on S plus the function act on the derivative. Okay? So that two statements are equivalent. So this is an infinitesimal version. If you integrate, then you get back that version. Okay? And sometimes people write it equivalently as a connection. It's a map from the zero form with value in E to this one. So just putting the dependence of vector field here, satisfy the same property. Okay. Satisfy that D of Fs is a df S plus F ds. Okay, so Lefschetz rule. Okay, so that's the connection, and you want so connection can differentiate E. Hermitian metric is a symmetric tensor of Hermitian symmetric tensor E, so you can differentiate that. Okay. Yeah. So this is assumptions. So there are lots of connections with this property, many connections. Okay. However, if X is a complex manifold, E is a holomorphic vector bundle. Okay, I just told you that holomorphic vector bundle look like a connections because when you say a bundle is holomorphic, meaning that you need to know how to look at the differentiation, holomorphic differentiation, d bar of the function sections. Right? So this structure is the same as a operator. You need to know how to differentiate the functions, but this is only d bar direction, so you only go to the z bar direction. So this is those directions which look like dz bar direction. No dz direction, dz bar direction of that. And again, this is a differentiation. Of course, it has a similar property that if you have a functions times s, that is a functions d bar s plus d bar of f times s. Okay, notice that this is s is a section, but f is just a function. So this has nothing to do with E. Okay, so this is just something about the manifold, background manifold X. Okay. So notice that these two conditions look very similar, except that this one is relating the zero-one part. This is the whole of that. Okay, but then you also require that look like the curvature, look like this curvature to be zero because you need it to be a holomorphic complex manifold. Okay. Yeah. So this is the observation by Atiyah, Hitchens, and Singer that in this case, this structure, okay. So so statement is X is a complex. So if you have a vector bundle, and this is a complex manifold. So it itself already have d bar for each function only. Okay. A holomorphic structure on E, which is how you should define this type of operator, is equivalent to saying that you have a connection such that, okay, so connection is something from 0 to one form. Okay? So, a complex value, one form. Then if you project it to the 0-1 part, and then we call this compositions. So this is just project to the 0-1 part. And then you look at this as, we call this as 0-1. Okay? And having this is because the manifold is complex. Okay? So because this is 0. And holomorphic structure is you can find connection whose 0-1 part square is 0. Because then you just call this as a d-bar operator. Okay? Because we're just rephrasing this statement just because this is same condition. Okay? Okay? Because then once you have that, then you just define the holomorphic structure by the 0-1 part of that. Now, if you have the following, if you have a holomorphic vector bundle, so this is a complex manifold, and this is a so you have a holomorphic vector bundle. So this one is a simple, so it's one structure. Okay. If you also have a Hermitian metric on the bundle, then there exists a unique connection on the bundle satisfy the two properties such that the 0-1 part is this, and then the second one is it preserves that. Okay. And in a way, this is obvious because you want to define a connection. You already know that the 0-1 part of the connection, no choice. Okay. Now the question is, how do you find the 1-0 part? And this condition telling you that the 0-1 part, 1-0 part are Hermitian conjugate. So once you have the 0-1 part, your Hermitian conjugate, you get a 1-0 part. Okay. Reason? Okay. Because these conditions is the same as saying that for any two vector field, if you look at V1, V2, so maybe S1, S2, so you will choose some section of the bundle. Okay? So this will become a complex number now. Okay? A function, complex function. And then if you look at the differentiations of that, that is the same. So this is a function, so you can differentiate functions, you get a one form. And that is the same as you look at this one. Why? Because this one is 0. So therefore, when you differentiate to this whole thing, you have to differentiate h, differentiate s1, differentiate s2. Differentiate h is 0. So you only get left with differentiate s1 and differentiate s2. Okay? So that's the same. Okay, so now you project everything to the 0, 1 part. Okay, so project everything to the 0, 1 part. Okay, so this becomes 0, 1 part. Now, because this is Hermitian, this is complex linear, this is anti-linear. So this is 0, 1 part, this is 1, 0. Okay, so if you already require that, well, this part of the connection is determined. So this formula tells you that now this part of the connection is determined by this formula now. Okay? Because you want to know this, it's the same as you want to know this pair with any of S1, which is completely determined by d bar and h. Okay? So that formula, so therefore having h and d bar e completely determines the 1, 0 part. No choice. Okay, so that's the proof. And these are called the chain connections. So let's continue from here. Let me just write below here. Okay, so now we're in this setting. We start with a complex manifold. We have a Hermitian metric. So you already require the connection to have 0, 1 part to be this. So the metric will determine the 1, 0 part. So that determines this one. Now, so I compute a curvature for that connection. So that the curvature, which is the same as if you do it twice, so that has the property that they have the 1, 0 part twice. And then you have the 1, 0 part, 0, 1 part, and 0, 1 part, 1, 0 part, and then the 0, 1 part twice. Okay, so this is in where? This is in omega 2, 0 with value in X endomorphism of E. In H2, right? So as I mentioned, curvature is once you read in two directions, you get some infinitesimal deformations. Okay. So this one, each vector space, a fiber is really endomorphism of the fiber, which is CR. Okay. But CR has a Hermitian metric. So therefore, inside that, you have a UR here, meaning that those are endomorphism which preserve the metric infinitesimally. So these are Hermitian symmetric matrices. Okay? So the corresponding one we usually write it as a joy of E. Just a notations. So that sit inside endomorphism of E. So these are all those endomorphisms which preserve the fiber-wise metric infinitesimally. Okay, so each fiber, abstractly, this is just like all matrices. These are all Hermitian matrices. Okay. So this is where the curvature is. This is it sit inside here is because the connection preserves the inner product. So therefore, if you go around, still preserve the infinite product. Infinitesimally, the curvature preserves the inner product. So therefore, the curvature sit inside UR inside GLRC. Okay. All right, so this is a general statement about when a connection preserves a metric, the Hermitian metric. And now, because you have a complex structure, this is split into 2, 0 part, and then a 1, 1 part, and then a 0, 2 part. Okay, so two form has all this decomposition, DC and DC bar components. Now we already have this one is 0. This is because this is a holomorphic structure. So that's none of this. Okay? And these two are Hermitian symmetric, conjugate to each other. So this one is 0. This is how we define D1 0, right? You define this D1 0 via Hermitian conjugate of 0, 1. Okay? So this one is 0, and that one is also 0. Because these two are Hermitian conjugate to each other. Okay? So therefore, the curvature is completely a 1-1 form. Okay, let's write it down explicitly. In local holomorphic coordinate. Okay, it's important that we are choosing holomorphic coordinate. It's not the Hermitian coordinate, meaning that locally, this bundle over X, locally you write this as C with small open set. Okay, so this is just a local Cn, and this is Cn cross Cr. Okay, and then the D bar structure, the standard D bar structure. Okay, so whatever D bar here is the standard D bar on Cn. Okay. Let me just tell you the answer. And so in particular, the 0-1 form, the 0-1 part is exactly D bar by construction. Because this is D bar E, which in holomorphic coordinate, this is just the usual D bar on function, holomorphic on function. Anyway. Okay. But the metric is not standard because we trivialize holomorphically, not trivialize metrically. Okay, so the metric is not. So therefore, the metric is really a metric on CR. Okay, so the metric you can write it as a standard metric on CR up to a matrix, right? So the metric is up to some matrix called usually called small h. Okay, let's just write it as bigger h. Okay, a R by R matrix. Yeah. If you do that, then let me just write down the answer to this exercise. Okay. Okay. In this case, the connection is the same as the usual D. This because the 0-1 part is already fixed, so the only thing has to be 1-0 plus D plus H inverse DH. Okay, and then the curvature is D bar of H inverse DH. And clearly 1-1 type now. Okay, so these are a matrix, R by R matrix with depending on the element in R, Cn. Okay. So they are important formula when you really explicitly want to do computations. Okay. And notice that if this is a rank 1, then this is a number, and this is just a D of log H. So if E is a rank 1, so 1 by 1 matrix, this is our setting, rank 1 lie bundle. Okay. Then curvature, so write what is L, as I mentioned, over X. Then the curvature, in this case, will be a 2 form of X with adjoint of L inside endomorphism of L. Okay, but this is a rank 1, so this is the canonically trivial. So this is really the trivial Lie bundle. And then in this case, this one is really the purely imaginary, trivial purely imaginary Lie bundle. So curvature is really an honest two-form imaginary value in this case. So then we usually look at, consider a real form, then we usually look at I over 2 pi of F. So that would be an honest real form. Two pi is a normalization, so this, at the end of the day, that will be the first Chern class, integral class. Yeah. So at the moment, it's not important. So this, okay. So here's the definitions. So L is called positive. If this form, let's just give a notation, omega. Okay. If omega is positive, it's a two form being positive, meaning that that is for any vector, omega of V, complex vector, V bar is positive, non-zero. Just define a metric, okay? Hermitian metric. So Hermitian point. Yeah. So such manifold will be called Keda, basically. Okay, so that is part of the statement in the quadrilateral theorem. It says that, let's recall that. Is if X is a complex manifold, okay, X can embed inside some CPN. If and only if there exists a positive Lie bundle on X. Okay? Meaning that you have a holomorphic vector bundle with a Hermitian metric, and such that the curvature is positive. Okay. So first of all, here is an example. The CPN is positive, the bundle. Okay. Example. Okay. CPN, again, the definition, this is all the one-dimensional subspace in Cn plus 1, which you can identify with, you take away the origin, and then you divide it by C star. Okay. Because it's an exhibit as a family of Lie, so it naturally has a family of Lie. So meaning that each point here is a Lie. So this is one-dimensional vector space. Okay. So call this Lie bundle O minus 1. Okay. So this is called tautological bundle, the name of that. Okay. And O1, OK will be definition, will be O1 tensor itself K times. So in particular, O minus 1 will be the dual bundle of that. So here, notice that what is O minus 1? Well, this is space of all line. So for example, so this space has a map to Cn plus 1. Okay, let's just draw a picture like n equal to 1. Okay, so this is CP1, this is C2. Okay, and this is all the line in C2. So an element here is a line. Okay, and then you attach the corresponding line upstairs, and that call it O minus 1. Okay, so this line is this line. Okay, you choose another line, you choose another one. Okay, choose another point here. Then you get another fiber. And you see that the whole C2 is filled up by all this line, exactly 1, unless you are at the origins. Okay? So therefore, this map, except the origin, this map is isomorphic. Okay? Unless this is the origin. Well, if this is the origin, then every line passes through the origin once. Okay? So therefore, this particular space has the following property that if you look at this minus the origins, or this one take away the 0 sections, they are isomorphic. Because all the line, if you take away the origin of the line, okay, then they all exactly fill out the C2, except the origin. Or if you're at the origins, then the preimage of the origin is exactly this whole fiber. So this is an explicit description of what we call a blowing up of a space at a point. Okay? So if you know it, then this is just sometimes people write this notation. It's a blowing up of Cn plus 1 at the origins. That means that you don't do anything outside the origins. At the origin, you replace that by all the directions through the origins. Okay? That's usually what we call the blow up. This is explicitly this map. So this fiber is mostly 1-to-1. This is a degree 1 map. Both fibers 1 point. But this is not. This is all the fibers C. Okay. Okay. It's clear, right? So now this one clear. So therefore, O1 has clearly has a standard inner product. Because you just use this metric here. The standard metric on C2, Cn plus 1, induce so you use the standard metric here. So therefore, restrict to each line. Oops. Pass for the origin. Restrict to each line, give you an inner product on the line. Okay? So therefore, the metric on so this one come from the standard metric on the space. Then this one has a standard inner Hermitian metric. Okay? It clearly has a standard holomorphic structure. I mean, this is a holomorphic structure. Okay? And so in this case, okay. So this one, and then together with D bar L, okay, then you get a standard connection, okay, the chain connection, okay, chain connection, and the one I just mentioned, and then curvature. So in this case, explicitly, the curvature look like this. There's maybe I here, I may forget. Okay, it's D, maybe D bar, but that up to a size something here. Okay, log of 1. So if you, so this is the answer. Okay, maybe I put it as an exercise. So if you choose the coordinate here to be Cn with coordinate Z1 up to Cn. Okay, and this are called the forbidden stated metric. Of Kähler form or something. On the manifold, on CPN. Okay. So you might wonder, why do I have to choose this coordinate? You don't have to, because the following. What do you choose other coordinate? The point is, you don't have to, in the sense that you don't have to do it. You just do it here. So CPN, you can choose a homogeneous coordinate, Z0, Z1, up to Zn. And these are equivalent to if you scale it by non-zero constant. So if you fix the chart to be C0 to be 1, then that will be this so-called inhomogeneous chart. So these are so-called inhomogeneous coordinate. So this is just an honest coordinate chart, and this is coordinate up to scaling. Okay, so this is called homogeneous coordinate. Then this one is the same as dd bar log of z0 square plus z1 square plus zn square. Okay, you wonder, oh, these are different. You certainly have this. Well, the thing is, you can divide this by c0 square. Dividing this by c0 square, or that cancels this effect, to make it homogeneous. Does not matter, because this one does not matter. Because this is a dd bar locally of a holomorphic function square. And this is always 0, because this one is called polyharmonic. This is a dd bar of log z0 plus log c0 bar, right? Because the norm square is z times z bar. Okay, but this is holomorphic. This is q by d bar. This is anti-holomorphic. This is q by d. Okay, so this is 0 because d bar of that is 0. We dq this because this is anti-holomorphic. Okay, so you're adding this one or not adding this one does not matter, because this is different, because this is not square of the holomorphic function. This is sum of those. Okay, so you don't have this effect. Okay, so therefore, when you put this, you can write this in homogeneous coordinate. So therefore, at the end of the day, you just write in this way. So then this is just don't have to choose any coordinate chart. You just do it exactly in homogeneous coordinate. Okay, so this is how we usually write this. Okay? Or in a homogeneous coordinate. Okay. If you want to be even more explicit, so on CP1, if you are looking at this particular chart C with coordinate Z, then this one is maybe up to I. It's dz bar over 1 minus c square, 1 plus c square. Oh, just differentiate. That's what you get. Well, for example, you see that if you change to w equal to 1 over z, then you get exactly the same expression. It's a simple exercise. So you can use this coordinate chart or the other coordinate chart. So now we know that this bundle C01 on CPN, explicitly, this is an example that this line bundle is positive. Okay. Now, sorry, if you have a complex submanifold inside CPN, call this map F, and you can pull back this bundle call it L. So what is a pullback of a bundle? Right? A bundle meaning that you have a family of vector space. And now you want to get a family of vector space. How do you get the vector space over a particular point while the image has a vector space over that point? You just use that one. Okay? So that means that pullback bundle, meaning that the bundle over a point here, you just use the one in the image. Okay? Just is defined to be the fiber at the point fx. Right? So just use the vector space in the image. That's what you call pullback. So you can pull back this one. Okay. And you can pull back the connection, because the connection is a trivialization along each path. So how do you trivialize along a path here? Well, you look at the image of the path, that will be a path there. And you have a trivialization there. That is the trivialization here. Okay, so it's tautology, basically. So therefore, here you have this standard connections, and then you can pull it back here. This O1. You pull it back, you get a connection. You get a connection for this L. Okay. Everything just the same as before, because the connection is really the connection here, so the curvature is really the curvature here. So therefore, the curvature of this connection is also the curvature pullback of the curvature there. So the curvature of the CPN, you pull it back, it's the curvature for that one. It's the same reason, because everything comes from the thing from the image here. Okay? And this one is positive, and the map is injective. So this is positive because this one is positive. Well, if the map is a constant map, then the pullback is not positive. The map is injective. Okay, the map is embedding. So therefore, whatever here is computed here. Okay, it's embedded. Okay. So this is a simple part. We're just saying that if you embed inside CPN, then you obviously has a positive line bundle. Okay, so the whole film is to prove the converse is also true. Okay. So if x inside CPN, then that exists a positive line bundle on x. In fact, that line bundle is the pullback of O1. Okay, so you need to prove the converse. So embedding problem. So you want to embed inside some space. First of all, let's say if you have a space, you want to get a map first. Okay. Let's say on Cn. Let's just call that V. So let's say some vector space abstractly. You don't have to be choosing a specific coordinate. Let's say you want to. That is the same as you have n plus one different function, right? This is the same as f. Okay. What are those functions? Well, these are really the coordinate function on V. Okay, so those are pullback of coordinate functions. Okay, so this one are exactly all the coordinate functions on V. Right? This function is just really that function. That's it. But if you want to embed, you want to get a functions to Cpn, which is Cn plus 1 minus a point quotient by C star. You have two issues. One is this, you have to avoid the zero, and this is only well-defined up to C star actions. Okay, so two issues. So you can write this as F0, F1. So you write this as V minus origin quotient by C star. Up to Cn. Okay. First of all, you have to avoid zero, so you have to be cannot be zero at, simultaneously. Okay, without common zero. Okay, meaning that you have to avoid this one. Okay, and the second thing is these are not functions, because this is only well-defined. The whole thing is well-defined up to C star. But if you think in this way, this really are element come from element in V. Okay, what is V? Okay, so in this case, V star. Okay, V star is the following: is exactly all the holomorphic section for O1. Say V star. I mean, this is Z1 up to Cn. Okay, so that means that like Z0 up to Cn. So the coordinate function is not really well defined in the quotient, but it's not a function. It's a section of that. That is essentially encoding the twisting. Okay, so that means that you want this, and then such that you want the f, each of these fi lie inside X, some line bundle, and the line bundle is exactly the pullback bundle. If you have a pullback, if you have a map F, okay, then Fi will be defined there. Okay. So let me just say it again here. That means that if you have a bunch of sections here, so that if you have a bunch of sections of some line bundle, and they don't have common zero, then you can define this map like that. Okay, so let me just say this one right here. So that is if you have F1, F0 up to Fn, which is a section of subline bundle, okay, without common zero, okay. Another way of saying that without common zero is that if you have a vector, so that means that at each point, at every point, then the fiber is some vector space. In this case, it's one-dimensional, but in general, it could be any dimensions. If you have a bunch of vector, a lot of vector, if it is one-dimensional, they are just multiple of each other. They are either zero or non-zero. So without common zero, that means at least one vector is not zero. So that is already generated vector space. So in higher dimensions, if this is not Lie bundle, the corresponding statement is that they're globally generated. Meaning that at each point, all these sections, at every single fiber, the section will form a generator of the vector space, okay? Globally. So it's called globally generation. In general, for bundle. Okay? Okay, so that is this part. Now, the second question is, can you get an embedding? This is just having a map, okay? So F is the embedding, meaning that you have enough function to separate points, okay? To separate adding 2 points. Okay? That means that is for every point, for every 2 distinct points. Okay? Then you have some combination of this, so that this value and that value are distinct, are different. Well, of course, that is what we mean by embedding. Okay? That is also that is necessary. You also have to assume that the 2 point could be infinitesimally close, as I mentioned explained last time. And that's the same here. I mean, that whether the 2 point separate 2 point is really nothing to do with Rn or Cs. So this is also the same thing. You find 2 sections which separate. This nice thing. Okay. Now the question now is, in a smooth setting, this is very easy to do it because it's always okay because of partition of unity. Because locally you can do it and then you can group it by cutting it off, die down, and then local function become global functions. Okay, so you have many functions. Because locally you always have enough functions, but local function may not be global function in the holomorphic case. So smooth case, but this will really tell you that local function, you can look at it, shrink a little bit, become global. So you always have a lot of functions in either case. Okay. So let's say in this case, it says the following. This case, it says that if you are given any Lie bundle in a smooth setting, okay, then you can always find lots of functions, sections, smooth section now, okay, without globally generated or without common zero. Let me just say globally generated. Then you get an embedding inside some CPN, and so that this is O1, and this is the function F. This is L. The original L becomes the pullback of that one. You can always do that, same argument. But you can also always add more sections. If you add one more section, then just put inside bigger CPN. And this one continue to map to O1. Let's get one more function. It's still bigger and bigger. You can keep on continuing. You just keep on adding more and more functions. The statement is eventually this is independent of the choice of sections. So, okay. eventually, you get this map to CP infinity. Okay, this is you can keep on adding it. Okay, it's independent of any choices by the adding more of everything. I just keep on adding up to homotopy. So that is if you look at all the line bundle on X up to isomorphism, so this is L, okay? You can always map to the homotopy class of map from X to CP infinity, and this map is well. So you send to all this F, with infinite many of those functions, and this is a bijection. So these are called classifying space for line bundle. Okay. And similarly, if you look at rank R complex vector bundle on X, so these are countable CW complex, if you worry. That you can exactly do, you choose sections which are globally generated. So same argument will map to the map to the correspondence of R space inside R plus n, you send n go to infinity. So sometimes we write it as infinite correspondence. So these are called classifying space topologically. Okay. And that play an important role, as I mentioned, with so-called characteristic classes. And cobordism theory too, we'll explain that later. Okay, so now what we really now want to do is the following. Whether you have enough holomorphic section, that's the question. So now, given this is a complex manifold, compact complex manifold, and this is a holomorphic line bundle. And the question is, we want to use ampleness to assert that there exists enough. There are lots of sections, holomorphic sections. Okay. How many you need? Well, you need them to get a well-defined map that's globally generated or without common seal, but you need more to separate points. Okay, yeah. So, okay. Try to construct a lot of holomorphic sections. Right? That's the A. Okay. So, what is a holomorphic section? Well, it's locally. Locally, it's just a function. Right? Locally, it's just a function, and this is holomorphic function. Right? That's what holomorphic means. If you do an analog in a real case, if you have a manifold, and then with a function, Now that analog will be constant. Right? A holomorphic section, a function, analog will be holomorphic, a constant function. And if you look at all the constant functions, assuming the space is connected, so that's just R. Okay? And in fact, you can continue to look at this instead of function. You can look at what form and all this. So, in fact, you can consider the following: omega, all the functions, and one form, and two form, and let's say the manifold is n dimensions, n form. Okay. So element here would be locally look like some functions on the x variable, and then some dxi, some combination of those. This is the one form. They differentiate. So d squared is 0. Okay. And so you can look at the kernel over image. So d squared is 0. So image inside kernel, and then you look at kernel of D over image of D at the K form part, and that is what we usually call the K-free round homology. Okay, so you get an analog here. It's H0. And these are just constant because this is just nothing in the image. So this is kernel of D. So these are just constant functions. And then you have H1 and Hn. I'll explain that later. That of course this is one dimension in this case, but one important property in algebraic topology is the alternating sum of its dimensions has a nice description. It's called the Euler characteristic. And you can also write it as the integral of the curvature in some expressions called the Pfaffian. At the moment, it's not very important. The important is this is a very topological thing, which depending on the curvature of the manifold. Integrate on the M. Okay, these are called the Gauss-Bonnet formula. And you can have this exact, you have an analog in the holomorphic setting. So if you have a bundle here, then you can look at H00XL. If this is d bar equal to 0, that's a holomorphic function. But you can d bar will lie inside CL1 here, and then you keep on doing it. So X is complex n-dimensional. Okay. And now holomorphicity is used now because the bundle is holomorphic. It's exactly the same that this is 0. This is because the bundle is holomorphic Lie bundle. Okay, you can do the same thing. And also, the first term, so you get this is called the Doboko homology, which is the same as you look at the kernel of an image at the K level. Okay. And the one that we want is H0, in particular H0. It's the same as all the holomorphic sections. This is the one that we want. We want to find lots of holomorphic sections. The same here, I have a formula here that look at the alternating sum of the dimensions. Is the integral of some expression in terms of the curvature. It's called the taut form of the curvature. So this is the curvature for the manifold X. Okay, so curvature for X. But you also have L here, so it also involves the curvature of L. Okay, and the expression in terms of curvature of L is so remember the curvature of L is just a two form. One form. So this expression is e to the I over 2 pi times f. Yeah. Okay. And then we want to find lots of this section. Okay. So the aim is the two things. One is to make sure that this whole thing is very large. Maybe I just write this down. This is the dimensions. Let's just write the dimension. It's a small h. Okay, this is the dimension of this cohomology. Minus 1 plus h2. So the aim is to make this very large and then to also make all this 0. Right? So the first, to make, so the first, okay, so the first is, step, the first step 1. Make this large, make the whole very large. The second one is to make all the high cohomology vanish. So H0 is very large. Okay, yeah. And okay. So how do you make it large? Well, both of them is using the fact that the curvature is positive. Okay, how? Well, so if you allow this to some power, sorry, let me call this L, yeah, because I have to use K there. For no reason. Okay. Okay. So if you tensor this to power k, then the curvature is just multiplied by k. Okay. And this expression here, turn out that is that the other class is a 1 plus some curvature for. So these are all relating. Just roughly like that. So this is maybe taut 1, just right here, taut 1, taut 2, and so on. So these are depending on the curvature. The whole point is to start with 1. And this is a 2 form, this is a 4 form, this is a 0 form, and so on. Okay. So why does it help? Well, because you just write this down, you integrate, because this is a complex n-dimensional manifold. So you have to only integrate a 2n form. Okay? So when you look at all the 2n form, well, let's just write this down. Okay? This starts with 1. And we only look at when k is very large. Okay? So how do you get k large? Well, you better have this term. The highest power of k is k to the power n. And then I forget this one, okay? F omega n over n factorial. Okay, if I over 2 pi or something. Just forget it. So the largest power of k, because we only care k is large, right? Is this term. Because you only integrate a 2n form. This is already a 2n form. The next 2n form is already k. You have to absorb some of this because this is the thing. You only use the 1 here. Okay. So all the other is lower power. So when k is large, this is dominating. So you don't even care about this. So all you need is this is positive. This integral is positive. Then you are done. This whole thing is very large already. Okay. You don't even need f to be positive. You only need to be the f to the power n on the average is positive. That's enough already at this moment. Okay. So that's called big line bundle. Okay. So this one is of the order O positive power. Okay. It's this. It's some positive number times k to the n and up to lower order. Okay. So therefore, when k is large, it's very large. So all you need is C is this one. So you only need this to be positive. Okay. In particular, L is positive will be enough. Okay. So that will make the first step work. Step 1. That is a lot big. Okay. The second step is to make all the higher order part vanish. So that is more important about the curvature. These are called the Cordova vanishing film. It's attempting an argument in a differential geometry, so-called Borna technique. Maybe later I will explain how to do that in general. But let me just tell you the statement is if f is positive, I'm writing down a loose form. Okay, so that already implies higher cohomology. There's a much more precise form. Okay, large. Okay, that's a very precise form for that. But let's just for the moment, that's important enough already. Okay. Yeah. So so this is using Hodge theory argument to prove this, and this in fact has a huge generalization using characteristic P, algebraic method, many other. There's a huge application in different algebraic geometry. But this is the beginning of that. Yeah. So that is that gives you the part 2. So I'm skipping the proof of doing this argument here, but just give you the favor. So now you have a lot of sections in terms of the number, but then you have to say that you have so many sections that generate and so many sections that separate points. Okay. Then in algebraic geometry, you can put those conditions into conditions on some other cohomology. To say that those cohomology will force the section to vanish somewhere, something like that. And then by letting k even larger, you can always still have many functions to do that. Okay? So basically the idea is this will be so many functions, you can have so many functions to do any behavior you want, basically. Okay? And then you can, for example, you can separate points. So that is not the complete proof, because this is the first class of the day. So second class. Okay. So that is the point the way to prove the Cordova. It's not the proof, but the way to prove the Cordova embedding field. Okay.
Why you require the line contents? For the hierarchy, we have some statements.
What do you want? But the aim is when is the manifold projective?
Yeah.
That is already enough. because you put it as a glass bond, eventually it's the same property. So once it's projective, then you kick in all this Kählerian property.
So if a vector bundle has positive curvature, you can also say that it is projective.
Yeah, because then you have a positive Lie bundle.
But it seems
It's a lot more difficult to be a bundle to be positive than Lie bundle being positive. Yeah, because the positivity in high rank, you require positivity in many, many different directions. Yeah. It's harder. It's a much stronger assumption to have a bundle positive. For example, as I mentioned last time, if the tangent bundle is positive, that has to be CPN. That's a Harshon conjecture proved by Mori or Fault or Siu and Yao's. Yeah. Okay, so now what we learned earlier in a smooth setting. Now we're back to smooth setting or topological setting. That's the same. So first thing we learned is the following: any manifold can sit inside some big. Okay, for every x, then sit inside some big space. How do you use it? Then what? I mean, psychologically, you feel that, okay, this more general class is the same as the original class. Psychologically, you feel better. But how do you really use that property to really understand topology of X? Okay, I'm going to use one more ingredient. So the whole chapter is used only two ingredients in a way. The second ingredient is we know all one-dimensional manifold. If this is one-dimensional manifold, possibly with boundary, then it's either a circle or an interval or some union of those. That's it. Okay? We're only going to use these two facts. Okay? Well, I'll show you some example of how do you use this fact. Let's use the second one. Now, if you have a manifold with boundary, so this is a manifold with boundary. So again, what is a manifold with boundary? Well, this is a manifold with boundary, meaning that locally, either it's something like Rn, meaning, so if you have a manifold with boundary, so locally this is like Rn, or look like this, okay? Or this is the Rn minus 1 cross R plus. Boundary, okay? So either this or that. Okay? Only two possibilities. So it's a benefit boundary. If you have a map from the manifold to the boundary, and when you restrict to the boundary, that map is identity. Yeah. The statement is not possible. Not possible. Proof. Well, let's take a space with some boundary. I don't care what is inside the boundary. Okay. Look at a point here. X. Okay. Take any point here. What is the preimage of the point? Okay. The preimage of a point. Let's say the point is good. Okay. And it turned out that there's a theorem called SAS theorem, meaning that almost all points are good. Okay. So this is an implicit function theorem argument, which I'm going to explain. Okay. So those are dense. Right? So this is a so-called SAS theorem. Okay, here's a statement. The SARS film corollary of that is if you have a map from an M2 manifold, and this is dimension M, this is dimension N, okay, smooth map, okay, smooth manifold, smooth map, and so on, okay. Then that exists a dense set, and then X in N regular. This is a dense set. Okay, those are called regular points. So these are called SARS film, such that these are calculus questions. So that the pre-image is as nice as you want. The pre-image is a manifold of dimension M minus N. Okay, it's a manifold of dimension M minus N. Of course, there could be bad points, but most of the points are good. Okay. All right. So we're done. Okay. So take a look at this. What is the pre-image of that? Well, if this is a regular, then the pre-image has to be a manifold with boundary now. So this is a one-dimensional manifold with boundary. First of all, this contains the point X, because when you pursue the boundary is identity, the point in the point X. All right, so as a one-dimensional manifold, how does it look like? Well, it has to be a circle or interval. So it could be circle somewhere, or it could be an interval. Okay, so it not stop here. So the interval has to go somewhere else. Stop there. It could have some other circle. Okay, it could also have some other interval. Immediately, it's not possible because this point, the image, this point called y, the image of y is y. The image of y is not x. Okay? The image at the boundary, every boundary is identity. So this one is equal to Fy, right? So that's a contradiction. Because we know all the one manifold is an interval that cannot stop here because the function is smooth. It's a regular function, regular point, so stop from here. And you cannot stop anywhere. Okay. All right, so let's look at another example. You look at the ball. Inside our end. Okay. And then let's say you have a smooth function on the self. Then it has a fixed point. This is called a Brouwer fixed point film. B-R-O-W. And it's very important in the study of partial differential equations, where D is some functions, infinite dimensional function of space, and there's some differential operator. You want to solve the differential equations or the integral equations, and then you need some estimate to make sure that this operator, usually integral operator, have some estimate on the image, and then you can find the solution, basically. So that was one powerful method in analysis. Okay, so I'll prove. So if not, I'll call this our function, f maybe. Okay. So if not, that means that if you start with any point, then fx is not the same as x. Okay. Then you can draw a line. Cannot draw this line. You have to draw that line going backward. Yeah. You draw the line from fx back to x, and then continue to hit this, and then call this point fx. Okay. So if not, then you get a function from the ball back to itself. So you send this. This is the capital F. Because these two are different, so going back, and then you eventually hit the boundary and call this fx. Okay? And then you get the fx. This is the definition. And that satisfies the problem what we had earlier. This one satisfies the property that it's still smooth, and f restrict to the boundary is identity. Because if you start boundary, you go at whatever, you come back to here. Okay. So get a contradiction. So therefore, it has to have a fixed point. All right. Sure. If you have a smooth map between two odd manifold, if I don't say with boundary, then it's closed manifold, I say. Okay. The same dimension, for the same dimension. Okay. Then you can get degree of f. Which is defined to be the number of points in the preimage of some regular points. Well, Sarstrom said that lots of regular points, to choose a regular point. And so the preimage has many points, but then you have to count with orientation. That means they are plus or minus 1. Okay, so all these are. So these are plus minus 1 count. Okay. So if you do not know orientations, then that number will be either odd or even. Okay. Otherwise, this is number. Now, the question is, why is this well defined? So this is well defined. So you want to say that this degree is independent of y. So it's well defined, and also it's independent of f up to homotopy. That means that if you move the function f up to homotopy, then this is well defined. This is a space of all, let's say, smooth map or continuous map up to homotopy. Okay. And later we'll prove that if the target is a sphere, this is always isomorphism. It's called frame cobordism. All right, let's prove it here. Proof. First part, step 1. Okay. You want to say if you have different point, okay? But instead of different point, let's use the same point but different function first, okay? So the first thing is you have two functions which are homotopy from the same space. But we choose a fixed point which are regular in both f and g, okay? Okay, what is then the pre-image of, so instead of moving the different points, let's look at the same point but moving the function up to homotopy. So this means the following. This means that you have a family of functions starting from f to g. So f restrict to m cross 0 is f, and f restrict to m cross 1 is g. Okay? That's what this means. Okay? So this. Okay? That's our move. The function is part of a bigger family. Okay? Moving from one to another. Our proof of 1. Proof of 1. Just because this one now we have boundary or this and that now. Okay? So but this is a one manifold. Well, that's the end of the proof. Because now this is one more dimension. Okay? So therefore the pre-image of a point is a one manifold. And then this one manifold, the boundary consists of these two. Okay? So therefore, one manifold is that the number of points are the same on both sides. Okay? So 2. Okay. Now you want to make the change of points in the change of functions. Okay? So the second statement is here you have a manifold with two different points. Then meaning here. So you have a manifold with two different points. Okay. Then you can find a function homotopy to the identity functions. And then they're all diffeomorphism. The whole thing. Is that clear? So think about that. This is you're in Mong Kok and lots of people, and then you see your friend here, and then you just want to go there and just start to push the people around you, and then you walk there. And that's the family of diffeomorphism. Okay? So first of all, that means that the diffeomorphism, you choose a path, choose any path, okay? And then you're not going to move things away from the neighborhood, okay? And then you just start to push all the people around you and then move from one to another one. This is the family of diffeomorphism. It's very difficult to write down. It's easy to see exactly what you do here. You just do this. Okay, the best way one can do it is we call it exercise. But we're just writing down exactly you're pushing that away. Okay, that's But then you get the freedom for your way. Because you're just changing different point to be different functions. Okay, it's the proof of the field. Okay, and then you start with a functions. Okay, and then you have two different points. So you use this h, which send the y to z. But this one is a homotopy to identity. This one will send y to y. Okay? So this one, hold on. So this send y to z, this one to y. So therefore, this one is homotopy to that one. Okay? Now, the pre-image the same. Okay. So number of ports. Okay. Yeah. And this is because H homotopy to identity, so this is the same as actual something. Okay. Or you can say that F H is homotopy to F. Okay. So simple proof. Okay, so far it's very simple. More interesting, I'll show you an example. A sphere with a non-vanishing vector field. If and only if the dimension is odd. Okay. All right, let's take a look. Let's say dimension, let's say n equal to 1, which is a circle. Okay, it's a non-vanishing vector field because you just like this. That called is V. So this is a vector field, meaning at every point you have a tangent vector, and there's never 0. Okay. And how do you get this one? Well, this one because you put it inside R2, which is S1 inside R2, unit circle, which is a couple of C, which has a complex structure. And what you do is this particular point X, and so this is a vector in C, and you just write this as Jx. That is a non-vanishing vector field. Okay? And you can do that in any odd dimensions, because if you have any odd dimensional sphere, that is a unit sphere in Cn plus 1, in a unit sphere, same argument. All you need to do is just do this. Okay? So a point in the sphere is really a vector, right, perpendicular to the sphere. So J of that will become tangent to the sphere. And that's never 0 because this is a vector of length 1. Okay? So take any element x, you treat it as a vector in C. V at x is just J of x, okay, for all x. And that's not vanishing vector field. And this is perpendicular to that, to the sphere. Yeah, so this is a perpendicular to that, so that's why it's tangent to this. So therefore this direction is, okay. But even dimensional sphere cannot do that, well, because you just cannot have such at all. Okay. Yeah. So if you have a sphere, and then you view it as a unit sphere inside Rn plus 1. It doesn't matter what dimension it is. Okay. So this is a point in the sphere is with a unit vector. Okay. And then the tangent space is exactly those things which are perpendicular to that. Okay. That is the tangent space. The tangent space is all those perpendicular. So if I say V is a non-vanishing vector field, okay. But that is here, right? So this is V here. If it's non-vanishing, you can just divide it by the length, and then you get a non-vanishing vector field of length 1. Okay? So without loss of generality, we can assume the length is 1. So what we know is that this is a vector field in length 1, and we know that x and v are perpendicular. So just saying that this perpendicular to is in the tangent vector field. Okay. So therefore, you get a map from from x to the sphere. To that one, Vx. Okay? This is saying that this is a vector of length 1. Okay? But it's also perpendicular to V, though. So the V perpendicular to x. That's what we have. Okay? So, okay, for each vector, you get a vector, another vector of length 1. So this is here. But this is in the tangent space, so this is this property. All right? So what is the contradiction if n is even? All right, so let's just draw the picture here. So pick any point V here, x here. Okay? What is V? Well, V is somewhere here. Somewhere along this line, okay? Maybe here. Because it's perpendicular to that. So V, well, this is a perpendicular to that. So Vx is somewhere here. Okay? And now you can draw the big circle. You go from this to the opposite point. So this is a perpendicular, right? So you go from here to the minus x. We draw one lower dimension. So if this is S1, let's say, okay, we know that getting any point x here, Vx is perpendicular to that. So Vx, we see this point or that point. Okay, somewhere here. In two dimensions, it's a whole circle of that. So x is this, Vx will be somewhere perpendicular to that. Okay? Well, then you can gradually move from x, you run by pi, and then you move to minus x. Okay? So Vx is helping you to create a family of a homotopy from the identity map to the antipodal map. Okay, so let me write it down. To define the following map, F, depending on theta. When theta is 0, and this is its identity, you send x to x. Okay? And then when theta is pi, then this is an antipodal map, which is minus identity. Send x to minus x. Okay? And in general, this is the map. You rotate by angle theta. Because in general, the big dimension, you do not know which direction to move to. I mean, you have a consistent direction. The V giving you a specific way to move from x to minus x. Okay? Like specifically, f theta of x is cosine theta of x plus sine theta of Vx. Okay? And this one's still on the sphere because this is length 1, they're perpendicular. So therefore, this is still on the sphere. Okay? I mean, obvious. This is just this. It's just you have the point in the perpendicular, you just move from x to minus x. Okay? Explicitly, that's the map. Okay? So therefore, the identity map, these are usually called the antipodal map, is homotopy equivalent to the antipodal map. I mean, you send north pole to south pole. I mean, opposite pole. Okay. This one has degree 1 because every point, the preimage is itself is 1 point. Obviously, it's 1. Okay. Now the question is, for sphere, what's the degree of the antipodal map? Okay. So then we give you an exercise. Just you think about it, then it's not difficult to see. This is -1 to the dimension n minus 1, meaning that if odd dimension, then this is 1. If even dimension is -1. Just show the picture, think a little bit, then you will see that. Okay. So that finished the proof. This is homotopy, so therefore degree has to be the same. We just show you. So therefore 1 has to be the same as -1 to the power n minus 1. So that force that n has to be odd. All right. So next we want to prove the Poincaré-Hopf theorem. Probably prove it next time. Let's just explain it first. So far, we only use one statement, which is the one-dimensional manifold is either circle or interval. Okay. Now we're going to use another fact that every manifold sits inside Rn. We need to use that. Okay. Okay, so this needs some argument. Previously, all these are just one-step argument. Now this is more interesting. Okay. So for any manifold, meaning closed manifold, no boundary. Just when I say manifold, mean with no boundary. Okay. Then if a V is a vector field, meaning that it's a sections of the tangent bundle. Abstractly, it's not sitting inside any space or something. Right? It's just a tangent vector field. Suppose it has only isolated zero. Okay. The zero can be very degenerate. That can be okay. It's not necessarily non-degenerate zero. Okay. So we suppose V has only isolated zero. Okay. That means that this set is a discrete set, right? It's a discrete set. Okay. This is discrete set. A finite set, in fact. The manifold is compact. Okay. So for each of these points, you can attach to how degenerate this is. Okay. So I'm going to explain this one. Then you have an index of the vector field at that's 0. For each 0 point, you can attach a index. And the theorem is the sum of all this index is independent of the vector field. meaning that depending only on the manifold itself, it's called error characteristic. It turned out to be the same as error characteristic. Okay. So let me explain the index first. So the zero, the vector field, for example, say locally, let's say the zero is the origin, let's say. So it could be, so R2. There's a lot of possible vector fields. The simplest one is it could all moving to the origin, it can all move out. You can be rotating, but you can be a lot more complicated possibility. So these are the kind of simplest one, obvious ones. Okay? Yeah. Okay. So what is the index? Right? So let me explain that. Okay. So let's say Z is 0. It's an isolated 0. Okay. So so therefore locally, so Z, you can treat it as you can think about this inside. So draw like this. So this is X, somewhere you have Z here. So you take a local chart here. Okay, so you think about locally, it looks like an open set inside Rn. Okay, think about that. There's some vector field here. So this is isolated 0. So this is a small ball. Let's say that become the origin. Okay, small ball of the origin. Okay, so you know that V. So this is 0 now. Okay, origin. So because the index is only local behavior, so we know that V of any point here is not 0. Inside this spot, take away the origin, right? Because we assume that that is isolated 0. So locally, nearby, there's no other 0. Okay. All right. So therefore, when you restrict to the boundary, okay, and then you send a boundary point x here to Vx. This is in Rn. Right? Vx is somewhere here. I don't know, whatever. So it's a map in Rn divided by the length. So that would be in a unit sphere. So you get a map. So it's a map from an n-1 manifold back to n-1 manifold. Okay? And you have a degree. And that's what we call the index of this map, or degree of this map. Okay? So let me show example. So Robert, prove that next time. All right, so let's say we have a space X. Okay, choose a vector field. Well, how do you choose a vector field? Well, take with a triangulation. Triangulations. Okay, what is a triangulation? Well, for example, X is a circle. And then you just cut it into interval, let's say. Okay, or X is a surface, then you break the surface into pieces of this. Okay, and so on. So you write as the union of simplexes as grew in a reasonable way. Those are triangulations. And once you have a triangulation, you do the following. At each so in this case, you have a 0 cell, 4 0 cell, 4 1 cell. So in this case, these are 0 cell, 1 cell, and 2 cell. Okay, And each of the cell, you pick a point, midpoint. Okay, so this is the one cell, you pick a midpoint. 0 cell, of course, that's that. So 0 cell, 1 cell, you pick a midpoint, 2 cell, you pick a midpoint, and so on. And so on. Okay, and write a vector field. Okay, so what is a vector field? And so in this case, this is 0 cell, 1 cell. Just draw like that. I mean, just 3 0 cell, 3 1 cell. Okay, so midpoint, 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 midpoint. Okay, just draw a vector field so that you go to this. Okay, and then it becomes smaller and smaller. Okay. So because at all these points you're turning the directions, so the vector field better be 0 and all these midpoint. Right? So at each of the midpoint you turn the directions. Right? So this you go to here, so the 2 different directions. Once you go here, you turn the other direction. So therefore, now you have all the midpoint will be a 0 of the vector field. Okay. So how many? What is the sum of the index? It's a number of cells. Okay. So first of all, and also you need to see that at the 0 cell, the index is 1. 1 cell, the index is -1, and so on. Okay. So you see that in this case, the sum of index. So first of all, so the one point is you choose such a you do the same thing here. Okay. So 0 cell, everybody come in. Okay. One cell. You take a midpoint of the 1 cell, they go out here, okay, and then go out here, and then the 2 cell, midpoint, things come in, and then things go out, and so on. Oh, you can't figure out what they mean. Okay, so in an even cell, all the vector come in, and the odd cell, all the vector go out at the midpoint. Okay, and so the sum of the index. So first of all, the 0 of the vector field exactly corresponding to each of the triangle, the cells. Okay, 1 to 1 correspond to the midpoint of the cell. Okay, maybe say midpoint. Exactly the midpoint of the so-called barycenter. Okay, the midpoint of the cell is exactly the 0 of the vector field, and the index is 1 or -1 is exactly corresponding to the dimension of the cell is even or odd. Okay, just see it locally. Okay, and so therefore, this sum of the indices, which is this topological number, is exactly the alternating sum of the number of k-dimensional cells. Number of k-dimensional cells. Which, if you are in the simplicial topology, that's what you call the H. Called the Euler characteristic. And first of all, this theorem already show you that whatever this triangulations, the counting number of cells alternatingly is independent of the triangulations. Okay, and that's all the Euler characteristic because this is what we do in the Riemann surface case. It's the vertex minus edges plus spaces statement. Okay, so that's an amazing statement, and it does require some proof, and the proof we need to use the fact that we embed the manifold inside Rn for some large enough n. Okay, all right. So let's prove it next time.
What's the relation of concurrent theorem and Gauss nature?
There's a curvature statement. There's no curvature here. But then you have to, it's closely related. See, the thing is, if the vector field come from a group action. See, the thing is the group vector field may not come from a group actions. Then this is a localization field. The localization of Gauss-Bonnet chain related to the Poincaré-Hopf. But that is a localization that requires that good vector field. And the Poincaré-Hopf is more general. Yeah. I mean, the thing is, if you want to do localizations, there are only two so you either, okay, there's spot localization. Usually the first argument is you have a compact group action, then you can do localization. Okay? Or if you have a holomorphic vector field, there's also a holomorphic version of localizations. But this is not in either cases. And this does not fit into any of the localization. In a way, this is also a localization argument in some sense. But it's related in that sense. If the vector field is nice, saying that this is holomorphic vector field, or this comes from a compact group actions, then you can that follow from localization of the Gauss-Bonnet chain.